Good morning. Whoa, sorry. My name is John Kemper. I'm a postdoc at Utah State University and was formerly here at UVM. It is my pleasure to introduce Dr. Andrew Schroth, Research Associate Professor in the Department of Geography and Geosciences and the Rubenstein School of the Environment here at the University of Vermont. Andrew is a talented and creative biogeochemist who received a PhD in geochemistry from Dartmouth College in 2008 and has since built a wide-ranging and cutting-edge research program focused on understanding how biogeochemical systems and processes are affected by global or regional environmental change. His work, as you'll see, is built on the innovative employment of in situ sensors and has been instrumental in demonstrating the great utility and possibility of these technologies. Andrew is a thoughtful advisor and wonderful colleague who has, on a more personal note, been a great mentor and friend to me as I kind of wade into the waters of my own career. In addition to his roles here at UVM, Andrew chairs the Lake Champlain Basin's Program's Technical Advisory Committee and is here today to talk to us about his work understanding water quality and its drivers across the Lake Champlain region. Please join me in welcoming Andrew to the stage.
Hello, welcome to Vermont. Jump to my title slide. And thanks for the introduction, John. What I was kind of asked to talk about today here for you guys is kind of introduce you to some of the novel water quality monitoring data sets that we've developed here in Vermont from two programs, one of which is the Lake Champlain Basin Program. That's a long-term monitoring record that goes back to 1990. And another is associated with investments from NSF EPSCoR through a series of Track 1 and Track 2 awards from kind of the 2010s. They were really focused on building kind of water quality monitoring infrastructure here in the state. And they're kind of very, very much linked to one another. Why I have CIROH in the middle of this is, of course, both of these data sets are kind of core components of our water quality CIROH projects. So they're very much feeding into what we're doing here. And I think also, just given what we heard from the Senator and Ed, this is kind of a good time for us to kind of celebrate these monitoring data sets, because obviously they're much harder to build than they are to break. So we should celebrate them and try and protect them in this age. So with that, I really wanted to highlight to all of you, welcome to the Lake Champlain Basin Program. And this is a really cool place, a really cool kind of natural laboratory to do water research. And there's a number of reasons for that. You can see that the lake is bounded by two of the larger mountain ranges in the northern Appalachians, in Vermont, the spine of the Green Mountains, and in New York, the Adirondacks. And this is kind of near where Ed was talking about Old Forge, which is in the western Adirondacks. You can see that the watershed goes into Canada, and I'll be talking a lot about that kind of northern bay that the Canadian border kind of splits in half. And then you can see that we also have some very interesting land use gradients in the basin. So along these lowlands, like where we are right now, we have our major population centers like Burlington, and then you can see that like kind of yellow line moving from south to north, trending along the shores of the lake, and that's what we refer to as the Champlain Valley, and that's where most of our kind of agricultural, that's all that yellow is kind of ag. And why this is all really cool from kind of a water monitoring perspective is that the lake itself has a relatively high watershed to lake area ratio, something about 19. So what that means is it's highly sensitive to both hydrologic and biogeochemical changes that we facilitate across the landscape. And so it's a very good kind of sentinel for changes that we're implementing on the watershed scale. It's also really cool, and you can see this kind of from the map, that it's kind of segmented as you move from north to south. And what that actually means is that it's almost behaves like 6 or 7 different lakes rather than one, all with different watershed lake interactions, different ecologies, different biogeochemical dynamics, different water qualities. So that makes it a really cool kind of natural laboratory to do a lot of this kind of watershed lake research. The other advantage we have is what I mentioned earlier. We have these comprehensive monitoring infrastructure that scientists can leverage to study these dynamics across kind of time and space, and we'll get into more of that in subsequent slides. And then there's also this kind of optimal transboundary environment where that really facilitates a lot of the cross-disciplinary research that we've been doing and really kind of sets us up. And a lot of this is actually due to the Lake Champlain Basin Program, which I'm not the technical director of the advisory committee, but I'm a core member of that team. But anyway, that organization has a strong mandate to bring together kind of policymakers, watershed managers, and the scientists that are doing research on the ground, and really kind of facilitates that same kind of R2O, O2R framework that we emphasize so much here in CIROH. So this is a really nice system where we can do this kind of cross-disciplinary research to inform policy and management of the system while also being kind of cutting edge. So I mentioned the long-term monitoring program. This is a really cool monitoring program and kind of unique to the basin that goes back all the way to 1990. And you can see it really spans the entire lake. And those different lake segments that I was mentioning, the yellow circles are where samples are collected from the lake on kind of a biweekly basis from May through October. And the red triangles are the tributary sampling stations where samples are collected kind of across a range of seasons, flow conditions, to kind of get representative samples to inform loading estimates to the lake. So it's a really cool kind of watershed lake coupled monitoring program that goes back a long ways. We can see a lot of important changes to the lake watershed system, things like the lake's getting saltier over time because we're adding so much road salt to the land, or to the road network. The lake's getting warmer, stratification's getting stronger because of some of the warming trends that Jill talked about. And within this data set, they kind of collect, on each sampling event, they'll do sensor casts and they'll collect grab samples that are measured for kind of 25 parameters. So they're a relatively comprehensive suite of analytes. This is then kind of coupled with some more recent investments that we've made through the NSF EPSOR program, again, a program designed to promote infrastructure development and research competitiveness in kind of lower research dollar states. So both Vermont and Alabama are EPSCoR states. I think Utah bounces in and out of being an EPSCoR state. I don't believe it is one right now. But anyway, they have these Track 1 grants that are kind of a 5-year, $20 million awards that are again, targeting developing people, developing relationships, developing collaborations, and developing infrastructure like sensors in this case, to make us more competitive for future research proposals. We had 2 of these in kind of 2010s that both focused on kind of understanding the social ecological drivers of nutrient loading and cyanobacteria blooms here in some of the shallow bays in Lake Champlain. And then we had a Track 2 award, and these awards are designed to kind of facilitate partnerships and collaboration across EPSCoR states. And that focused more on developing watershed sensor networks using recently developed in situ sensors that can measure phosphorus and nitrogen at the same time at high frequency, so critical to looking at watershed nutrient loading. And we instrumented across the states of Vermont, Rhode Island, and Delaware in kind of land use and member watersheds of a forested and ag and urban dominated watershed. Another component of those projects was, it facilitated a lot of the collaborations that again continue to thrive, particularly under the umbrella here at CIROH, and really made us competitive for a lot of new grants. They helped us develop the Water Resource Institute that Beverly leads, and really just carved out a nice niche of kind of social ecological work in this water science space. A core tenet of those projects, and I really give Asim Zia and Chris Kaliba, were strong mentors for me in this space, and really that's like R2O, O2R engagement of stakeholders, so really involving the stakeholders from the get-go in the research. And then the other thing that was really neat is that we have these sensor networks developed on the lake and in the watershed, and they're now becoming some of the longest records of their kind in the world. So this is a really cool data set that's continued to be funded from different funding sources over the course of recent years. And the best part of these projects is, of course, the students that they educated. And I'm, of course, featuring 2 of my PhD students, Matt Vaughn and Peter Isles, who have an interesting feedback to the long-term monitoring program, and that Matt is now the chief scientist of the Lake Champlain Basin program, and Peter Isles is the lead Vermont DEC contact that runs the monitoring program for the state. So these guys have brought their knowledge of these sensor systems and the value of these data sets and the threats posed to the lake to those programs, and kind of serendipitously, they were in their positions when the basin program received a big boost in funding during the Biden era. And of course, what they did was try to modernize the monitoring network. So now not only is the monitoring network focused on those long-term grab sampling data sets, but they've purchased sensor infrastructure that they learned to work with under the EPSCoR grants to target particular segments of the lake where we were kind of, where we're seeing some more negative trends. And they've also actually incorporated our sensor networks from the EPSCoR project into the long-term monitoring program. So there's really cool feedback between those two monitoring programs that's facilitated by personnel development. All right, so I'm going to switch into a little bit of biogeochemistry. I'm not going to go into a lot of detail because I know we're not all biogeochemists, but I kind of want to tell the arc of this story as opposed to the fine details. But one of the main problems when it comes to nutrient loading in Lake Champlain is we're at a net imbalance, positive imbalance of phosphorus coming into the lake relative to what's going out. So there's much more coming in than going out. What happens there is that means the concentration of phosphorus is building up in the lake sediments. We refer to this as legacy phosphorus. And in these shallow systems, that phosphorus can become bioavailable and feed cyanobacteria blooms. We can look at sediment cores over time and see in these shallow bays when they went eutrophic. It turns out they kind of shifted from mesotrophic to oligotrophic systems, more low nutrient waters, to eutrophic systems over the second half of the 20th century. It's really as urbanization took hold in some of them and more so the intensification of agricultural processes. And so you can see that by buildup of that legacy phosphorus in the sediment over time in the sediment cores, as well as like bloom indicators associated with different proxies. So the systems went from mesotrophic to eutrophic over the 20th century. And of course, what that meant is that the EPA eventually stepped in and mandated that we develop what's referred to as the total maximum daily load, which is really trying to pull down some of these higher phosphorus concentrations. How they've implemented that here is actually developing target phosphorus concentrations for each of those segments. And I'm showing in the plot behind me, the red is when you're in exceedance of that TMDL. This is all based on that long-term monitoring program. And the blue is when the long-term monitoring program is demonstrating that we're below that threshold. The other thing to notice here is that this is, again, divided by these distinct segments in the lake because they have fundamental biological and geochemical differences. And so the targets are actually different thresholds depending on where you are in the lake. We're going to focus a lot on that one in the right-hand panel of the plot, right next to my EPA target concentrations plot, the Missisquoi Bay site, where you can see that we're well above that threshold consistently. And that's, again, because it has access to this legacy pool of phosphorus over time. But you can see, for example, where we were out yesterday on the cruise in the main lake, the targets are really low. That's a clear, oligotrophic, low nutrient waters. The targets are something like 10 micrograms per liter. Whereas in the South Lake, the target's 60 micrograms per liter. So wide variability, again, related to this interesting system, but then the EPA mandates these different targets that we have to reach to get improve impaired water quality. So the root cause of TMDL noncompliance is not subtle. Here I'm showing a time series of high-frequency phosphorus data in an agricultural catchment. Horizontal line is the Missisquoi Bay TMDL target, and then the darker line is orthophosphate dissolved phosphorus. The total line is total phosphorus. This is from those high-frequency sensors, and it looks a lot like a hydrograph, right, where you're seeing a series of fall storms pulse through the system. We're getting orders of magnitude higher phosphorus concentrations in the loading than what we need in the TMDL. So there's that long-term buildup over time. But in these shallow bays, we also have to deal with this internal loading piece. And we spent a lot of time under EPSCoR working on understanding the kind of chemical dynamics of this particular system. But the basic gist of it comes down to the extent to which we're seeing thermal stratification, when and where and for how long in the lakes. Missisquoi Bay happens to be a polymictic system, so it mixes really easily. It has a large area, but a relatively shallow depth, so it's like 3 to 4 meters. What that means is the wind can break down water column stability really easily. And so when we have low oxygen conditions, when we have oxidized conditions, phosphorus likes to stick to a mineral that's kind of looks like rust that you might see in your car. That's really stable under high oxygen concentrations, but if stratification forms, oxygen concentrations go down as bacteria consume oxygen in sediment. Those minerals dissolve, release phosphorus into the water column, and then in the shallow systems, it can be mixed up into the photic zone where the cyanobacteria can run with it and feed blooms. Cyanobacteria can also actually migrate vertically. They can regulate their buoyancy and go down and get some of this in these shallow systems. So this is a really important process in places like Missisquoi Bay. What does it look like in the data? Here's some plots from the long-term monitoring data from Pete Isles dissertation. You can see this is actually 2012. The red lines are 2012, which is when I started here. My first summer here, it was particularly hot and dry. The left-hand panel, you're looking at cumulative discharge of the Missisquoi River, and you can see from kind of July through August, it just flatlined. There were no events. And what we see is when we're looking at kind of 10 years of these data, that those were the highest concentrations of phosphorus in the lake during that entire record. So that's an internal loading signature. And consequently, we saw one of the most severe cyanobacteria blooms of the record during that particular year. We can then look at our high frequency data. And so this can tell us more about the drivers on the short term of the cyanobacteria bloom. This is some work we did with Donna Rizzo. And we're looking at clusters of high frequency data now based on conditions. And we start to cluster and I should mention the upper panels are phycocyanin time series associated with the cyanobacteria bloom. So when that black line goes up, the bloom is stronger. You can see 2012, the bloom was really strong. 2013, the bloom was kind of muted, and 2014 was somewhere in between. And then you can see the different kinds of conditions. We have cold, wet, and windy, and then peak bloom and stratified. You can see those peak bloom conditions were really what was driving the really high bloom during the summer of 2012. The dominance of kind of the windy conditions in 2013 really pushed down the bloom, like a conceptual model would suggest. And then those stratified conditions seem to be the strong triggers of the bloom. And so this is the kind of insight that really keys in on the importance of wind and the importance of having these high frequency data sets to kind of tease out these much shorter term drivers. Of course, the other thing that these data sets are really good for is developing process-based models, and we did just that under the EPSCoR project. This was spearheaded by Asim Zia, with Pat Clemens playing a key role in kind of tying all these models together, and we had lake modelers, Clelia Marti and Ahmad and Kareem Hanoun, who developed the model. It was a process-based model called AEM3D. Of course, to do this, we need to force the model with riverine inputs of nutrients, and we have a number of those models that are derived from the long-term monitoring record, one developed by Kristen Underwood and one developed by Peter Isles more recently. Of course, these data are particularly useful for calibrating and assessing model performance. What I'm showing on the right-hand plot is long-term monitoring performance of temperature, so the physics, the phosphorus, and the biology. The take-home point is we can get temperature profiles really well. We can understand the physics based on the model performance, but the biology and the geochemistry is a little more complicated, so we don't get quite the same model performance. We can also use the data from the high-frequency platforms to look at this, and you can see that the temperature profile, we're capturing those short-term dynamics associated with the wind fluctuations, which is obviously really important for studying the bloom. And then the bottom panel is phycocyanin again, which is the algal pigment, and you can see that we're capturing essentially the relative severity of the bloom in the 2 years and the timing of the bloom in the 2 years, albeit imperfectly. So this is a useful tool for studying this problem. That then allows us to kind of key in on research questions, and here's some plots of simulations. I think this is RCP 4.5 under the first track one, where you can see given climate change and legacy phosphorus in the upper panel, it's really hard, even with multiple different reduction scenarios going all the way to 64, even 80% watershed reduction, to meet your TMDL target for that system. And it's even harder to actually push down the blooms, right? And that's the green line, which is a 20 microgram per liter threshold. And it turns out that under that relatively low level of climate change scenario, even with like 40% reductions, you're seeing the blooms increase. And that's again because that red component of Pete's data set, that peak bloom condition increases in frequency as we change the climate. So what do we do about this legacy phosphorus? There's a couple of different options on how we address this, and it's basically we have to somehow disrupt our cartoon. One way that's common, and you see this in ponds and small lakes across the country, is we try and keep it in the high oxygen state on the right by something like an aerator that's physically mixing the system or introducing oxygen to the system. Another way is we try and get it off the rust and onto something that's resilient to low oxygen conditions, and the way that that's typically done is an alum addition or something else that doesn't respond to low oxygen. So you get it off the rust and onto the aluminum, then it's not going to respond to fluctuating DO, and you'll limit that internal load. And then you can try and dig it out, right, with dredging, but that's super expensive, especially on the scale of Missisquoi Bay. So we actually had a study that was funded by the Basin Program at the request of the International Joint Commission, to look at this with our model to see what kind of what could kind of be done about the internal load there. And we really came to the conclusion that the only viable treatment for Missisquoi Bay at that scale would be a chemical intervention, so something like the alum addition. And then we played around with our model to look at how that would actually play out in the blooms. And I should note that all of these things need to be done in concert with watershed reductions to be effective, or you'll have to just keep doing them over and over again. So you want to be getting the watershed under control when you're implementing these kind of more expensive in-lake treatments. And so this is what the output looks like. And this is a little bit of a complicated figure to walk you through without the pointer, but the circles here are just watershed reductions, and our green line is the target chlorophyll that we're trying to reach, 20 micrograms per liter, and the blue line is the TMDL phosphorus target that we want to meet. And you can see there's that sweet spot, right, the crosshairs. And then the triangles are a 50% reduction in internal load, and the diamonds and squares are essentially eliminating the entire load, internal load. And kind of we can see that there's kind of a sweet spot if maybe the triangles, that 50% load reduction is something that's viable, where we can get to like a 25 to 50% external load reduction, and then treat kind of 50% of the bay, and we're getting to where we've really massively improved the water quality of the bay. And that's because we've now targeted also that kind of summer internal load of the system. And it turns out we did another IGC kind of recommended study that was funded by the Basin Program, and that's really kind of the 25 to 50% range is kind of the maximum range where we can really, I think, reasonably achieve some of these watershed P reductions. The 64 to 75 is going to be a really big swing and tough sell. So, of course, when we see that, we can then go back and use our model output. Here I'm mapping the occurrence of low oxygen in Missisquoi Bay over the course of the summer, and kind of, if you squint at it enough, you can say, okay, if I was going to treat 50% of this, I can probably target those hot spots, those brighter colors where they're seeing more of the hypoxia. They're going to have more of the internal loading, and use our model to inform like where you would treat within the basin and do this kind of for the biggest bang for your buck. So powerful kind of application of this tool. The only thing I just wanted to mention, that's kind of all I've got on that topic, but again, this is informing a lot of other CIROH projects. John's and Mircea Morales-Vasquez are going to be providing a workshop later in the workshop to talk about some of our advances in watershed load, national water model, forced watershed loading of phosphorus, relying on these long-term monitoring data sets. We've got low-cost sensor development to try and expand the network of these at low cost. That's led by Raju Bhattareddy and postdoc Monterey Dehabadi. Asim's talked to you a lot about the various cyanobacteria bloom forecasting we're developing here at Vermont. And that's there's a graduate student, Mohammed Adil and Safwan Asa, who are also involved in that. Reach out to them when you're here. And then we also have a number of USGS CIROH folks that are led by Alabama and Utah State that are really focused on using these long-term and high-frequency monitoring infrastructure to improve satellite algorithms to assess bloom dynamics and suspended sediment dynamics in the lake. So lots of really cool stuff going on that's all related to these monitoring sets. Thank you for your time.